In section 4.2, we start working with rules to manipulate problems that have exponents. And the first rule we're going to learn is the product rule for multiplication. And the product rule for multiplication says if you're multiplying terms that have the same base, you add the exponents. For instance, I wrote an example that said x squared times x to the fourth is x to the sixth. This can be done by using the rule for multiplying terms with the same bases says you add the exponents and you leave the base to do the multiplication. If I wanted to show you why this rule works, the problem x squared times x to the fourth can be rewritten without exponents as a string of first two x's being multiplied and then a string of four x's being multiplied for the x squared and the x to the fourth. And when I look at what I have written here, when I write the problem without the exponents, I have 6 consecutive x's being multiplied, and that's what x to the 6 is. So that's kind of why the rule works. The rule works as long as the bases are the same. It doesn't matter if you're multiplying more than two terms. Like in the second example, I'm multiplying z squared times z cubed. Same deal here. I'm just going to add the exponents. With numbers, eventually I yank out my calculator. But for numbers, it works the same. As long as the bases are the same, when you're multiplying, when you have factors that have the same base but different exponents, we're going to add the exponents and fix the base. So when I did 3 squared times 3 to the fifth, I didn't do both. I didn't add the exponents times 3 cubed. I didn't add the exponents and multiply the numbers. I added the exponents and then I applied the exponent of 3 to the fifth. Notice if I would have written 9 to the fifth, I get that giant number, whereas 3 squared times 3 to the fifth, 3 squared times 3 cubed is 3 to the fifth, which is 243. So it's important when you're dealing with numbers to not multiply the numbers, just to treat the numbers like variables, fix the number, add the exponents, and then simplify. This is kind of a tweak of this rule. If I'm multiplying and I have variables, because multiplication is commutative, I can change the problem so that I can apply the rule. The problem 2x squared times 5x can be written with a times sign without the parentheses. And then because multiplication is commutative, meaning I can switch the order of multiplication, I can rewrite this as 2 times 5 times x squared times x using the commutative property of multiplication. And then I have generic coefficient multiplication of 2 times 5 and multiplying using the product rule for multiplication, meaning if I'm multiplying factors that have the same base, you add the exponents and fix the base. So the first chunk of problems will use this rule. So let's just do a bunch of these. These should go really quick. My problem 2, z to the fourth times z squared, I would generally just write an answer down, but to emphasize I'm using the product rule for multiplication. This is just going to be z to the sixth. The problem 4, my b squared times b to the first, I have to remember that that b that doesn't have an exponent written has an implied exponent of 1, and b squared times b to the first is the same as b cubed. Usually if a problem has a base that's a number, I won't write my answer with an exponent. I'll pull out my calculator if I don't know what the problem reduces to in my head, but 3 squared times 3, which is the same as 3 squared times 3 to the first. I'm multiplying. The factors are the numbers that are being multiplied have the same base, so I fix the base, I add the exponents, and generally I won't leave a number written with an exponent, so 3 cubed is 27. I'm using that button on my calculator. I type the number 3, I hit the button right next to the x squared key, then I type the number 3 and then equals. Problem 8, I'm multiplying 3 y's. That means 3 of the y's, 3 factors there, they all have the same base. So I'm going to multiply by leaving the base alone at y and adding the exponent of 4, 2, and the implied exponent of 1. That's the first of, I think, like 6 rules. The second rule has to do with when we're dividing and we have bases the same. It's called the quotient rule for division. And the quotient rule for division says if we're dividing terms that have the same base, we subtract the exponents. And the reason this rule works, like when I wrote here, x to the 6th divided by x to the 4th is x to the 6 minus 4. This is because the x to the 6 can be written as a string of 6 x's being multiplied. I actually count to 6. The x to the 4th can be written as a string of 4 x's being multiplied. And then I can cancel, 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 cancel. I canceled all the denominators, so I don't need to write a fraction anymore. And what I had left in the numerator is going to wind up being my answer, and x times x is just x squared. So this rule will work if I have multivariables as long as they're being multiplied. The problem x to the 4th y cubed over xy, I'm just going to subtract the exponents on the variables that are the same and keep the order that I have decided on. Similarly, if I had a problem like this, I put it in the section of a problem that uses the quotient rule because part of the simplification uses the quotient rule. To simplify a problem like this, I'm going to reduce the fraction 12 over 2. Cancel if you have the same exponent, so I would cancel the x's and then subtract the exponents on the y's. So I did 12 divided by 2 and got 6. Canceled the x's, subtracted the exponents on the y using the quotient rule for division, and that gave me my 6y cubed. And again, for these problems, usually I just write the answer, but to show you what I'm doing in problems in this grouping, I might show a little bit of work. So problem 10 is just this one step, apply the quotient rule for division. And you get y cubed. Number 12, just a one-step problem. This is just y to the 5th, y to the 5 minus 3 power, which is y squared. Works for variables as well as numbers. 3 cubed over 3 squared is going to be 3 to the 3 times 3 to the 3 minus 2 power. When you're doing division using the quotient rule, if you're working with numbers, the base doesn't change, just the exponents get subtracted. And this is going to give me 3 to the 1st power. For 14, I'd probably write 3 as my answer. Didn't write more complicated problems in this grouping for some reason, but we'll get to more complicated problems that have canceling and coefficients to deal with. In problem 16, the numerator has a base of 3 and exponent of 4. The denominator has a base of 3 and implied exponent of 1. I'm going to subtract the exponents, not change the base, and then I usually don't write numbers with exponents. I'll figure out what the exponent equals to, the number equals to without the exponent. If I don't have it memorized, I just yank out some technology. The next rule I kind of made an extension for. I made kind of this should be simplify using the power rule. So the power rule applies when we have parentheses that don't have any adding or subtracting inside. So the power rule is parentheses, and all the problems on the sheet right now have parentheses with no addition or subtraction. Maybe I should say nor subtraction. I don't know if that's correct grammatically. Inside. So if I'm presented with a parentheses that has an addition or a subtraction inside the techniques that I'm using right now, the rule doesn't apply. So the power rule basically, in its simplest form, says if you have a single variable with an exponent inside a parentheses, to clear the parentheses you multiply the exponents. So x squared to the third power is the same as x to the 2 times 3 power, which is x to the 6th. And if I wanted to show you why this worked, x squared cubed can be written as x squared times x squared times x squared, because something cubed means to multiply it by itself 3 times. And if I care to, each of the x squareds I can write as x times x. Ultimately, simplifying this problem as much as I possibly can without knowing the rules, I can create a string of 6 x's being multiplied, and that's what x to the 6 is. Works for numbers the same way. If I have a number inside a parentheses with an exponent and an exponent outside that parentheses, as long as there isn't any adding or subtracting inside the parentheses, you multiply the exponents, which I've already done over there. And then, generally I don't leave numbers written with exponents. I replace them with the appropriate number. If there's multiplication inside the parentheses and an exponent outside the parentheses, as long as there isn't addition and subtraction inside the parentheses, to clear the parentheses, I'm using the power rule of a product, the power of a product rule. And basically it just extends. What I did for the one variable, I'm going to do for multiple variables. So if I had x to the 4th, y to the 5th cubed, there's a product or a multiplication inside a parentheses and an exponent outside. Since there isn't any addition or subtraction inside my parentheses, I'm going to take each of the exponents and multiply them by 3. So I did x to the 4 times 3, y to the 5 times 3, and that would give me the x to the 12th, y to the 5th. I put this problem 5x to the 6th squared in this grouping right under the x to the 4th, y to the 5th squared, because I'm going to use the same power of a product rule to simplify. This is going to apply because I have straight multiplication inside a parentheses, no addition or subtraction inside my parentheses, and I have an exponent outside my parentheses. To use this rule, I'm going to multiply the implied exponent of 1 of the 5 by the 2, and I'm going to multiply the exponent of 6 on the x by the 2, and that's what I showed here. I did 5 to the 1 times 2, x to the 6 times 2. That gave me 5 squared, x to the 12th, and 5 squared I made into 25. On my calculator, to do 5 squared, I just type 5, and I hit the x squared key, and then I hit equals. This power rule works when you have a fraction as well. As long as there isn't any addition or subtraction anywhere, I can clear the parentheses by multiplying exponents. The y to the first divided by x squared all to the third power, I can do exactly the same thing. Multiply the exponents to clear the parentheses, and that's what I've done over here. Eventually, I start to get lazy and not show the multiply by 1. Pretty soon in the video, I'm going to say, when I'm using the power rule, I'm going to attach the exponent to any number or variable that doesn't have an exponent, and I'm going to multiply it by any exponent I see. So rather than writing a 1, multiplying it by the variable, when I use the power rule for a product or a power rule for a fraction, if a number or a variable doesn't have an exponent, rather than showing the exponent of 1 and then doing the multiplication, I usually say I'm going to apply the power rule by attaching the exponent outside the parentheses to any number or variable inside a parentheses without an exponent, and I'm going to multiply the exponent by any number or variable inside the parentheses that has an exponent shown, rather than showing the multiplying by 1. So let's apply that rule to a bunch of problems now. So problem 18 is just a simple one-step problem. I'm going to multiply the exponents to clear the parentheses using the power rule, and I'll get y to the 12th. Now I'm going to start doing the attaching. So if I have a parentheses with straight multiplication, the power rule allows me to shortcut. I'm going to attach the exponent to any number or variable that doesn't have an exponent, and multiply the exponent by any number or variable that has an exponent. This is because what I'm supposed to do is write the exponent of 1 that's implied, and then multiply the exponent outside the parentheses by the 1, and that's just silly to do. I know 2 to the 5th in my head. If you don't pull out if you don't, use your calculator to figure out what it is. I'm sure I'm gonna make mistakes in this video because I'm not checking my answers. For me, more often than not, it will take longer to actually check an answer than it will to do the problem. I'll do 21 because it's trickier than 22. In 21, I'm going to attach the exponent to the -2, and I'm going to leave the -2 in a parentheses. I'm going to attach the exponent to the x, and I'm going to multiply the exponent of the y. So attach to any number or letter that doesn't have an exponent, multiply by any number or letter that does have an exponent. If a number is negative, you should keep that number inside a parentheses if you're evaluating on your calculator, because the negative is part of the base. And my coefficient in my answer for 21 should be 4. So if I was doing 24, I'm going to attach the exponent to the -3, leave it in a parentheses because it's negative, attach the exponent to the x, multiply the exponent by the y, and numerically, that -3 to the 4th should be a positive 81. So my answer for 24 is going to be 81, x to the 4th, y to the 20th. I'll do 25 with you. In problem 25, this is going to be negative 3 attached to the exponent of 3 cubed, x to the 2 times 3, y attached to the exponent, so y to the third. I can do negative 3 cubed without my calculator. It's negative 27. So I'll just do that. These problems I misplaced. These problems I should have done when I was using the quotient rule. Those more complicated quotient rule problems, they're right here. Sorry, I didn't realize I had these out of order, but not such a big deal. I can deal with these. So I'm going to reduce the fraction 5 over 20. Five over 20 reduces to 1/4. So in problem 27, part of my answer should have a 1 in the numerator and a 4 in the denominator. And the x's, I have some flexibility. Either I can subtract the x's and subtract the exponent on the x's and leave the x in the numerator. And if I do that, I probably don't need the coefficient of 1. It turns out that that x, if it's straight multiplication in the numerator of a fraction, it's acceptable to drag that x off to the right of the fraction. And in that case, if I was dragging the x off, kind of removing it from the fraction, I should probably leave the 1 behind because I can't have a fraction without a numerator. I want to do 29 just because it's different than 28 and 30. So in 29, I'm going to reduce the fraction 24 over 12. I can do that without my calculator. It's going to be 2. The x's are going to cancel. And for the y's, I'm going to subtract the exponents and get y to the first. So for my answer, it's not going to be a fraction because there's nothing left in the denominator. The 24 over 12 turned into 2 over 1. It left a 1 in the denominator, but I didn't write it. The x's cancel, and then I have a y to the first. These next problems, I could have done at the beginning as well. They're more complicated product rule problems. For here, I'm going to multiply the coefficients and add the exponents on the variables. So in problem 32, I'm going to multiply the coefficients of 8 and 9. I'm going to add the exponent of 3 and 4 on the x. I'm going to add the exponent of 5 and 2 on the y. For an answer for 32, I'm going to make this 72 x to the 7th, y to the 7th. For my problem 34, I'm going to multiply the coefficients of 4 and 5. I'm going to add the exponent of 1 and 5 for my x's. I'm going to add the exponents of 1 and 1 for my y's. Any of the variables that don't have an exponent written have an implied 1. I could probably not show this and just write an answer down and be safe, but just in case you needed to see it, decided to show it. So I'm going to pause the video, and there's probably going to be 3 parts to this, I would guess. The next part is negative exponents, and those are a little trickier.